Welcome to this video. In the previous video we have seen how you can define vectors in 2D and 3D to describe physical quantities like velocity that have both a certain magnitude or strength or value plus a direction. And we've also seen that vectors are useful for that, and that with two vectors you can add them, and also with one vector and a number you can multiply them. In this video, we will look at the dot product. The dot product is an operation where you take two vectors and compute a number from them. And that number, called the dot product, is going to be very useful if you want to compute angles between vectors. And that is something that turns up in many applications. So let's look at a quick outline of this video. So what we will be considering is first the definition of the dot product. Then I will show how you can use the dot product to compute angles between vectors. Often we are interested in vectors that make a 90-degree angle, so they are called perpendicular to each other. If you have two vectors, they're always in a plane, and if you look in this plane and if they make a 90-degree angle, they're called perpendicular. And as an application, we will look at pulling a wagon. So if you have a wagon and you pull with a cord, then only part of the force that you put on the wagon will help move it forward. So we will have a look at that, and that will lead to the to component and projection. So they are important definitions in that context. So let's have a look at the dot product. So first, the mathematical definition. If you take two vectors A and B, so I have a vector A with three components, a vector B with three components, then what you do to compute the dot product, and the notation is like this, so A dot B, you multiply A1 with B1, you multiply A2 with B2, and A3 with B3, and those three numbers that you get, you just add them. So without doing any interpretation or why it is useful, just this is the way you compute a dot product, and we will show why it is useful in a second. So just a simple example. So if you have the vector 1, 2, 3 and the vector say 4, and let's put a minus sign in there just because it's a little bit more interesting, 6, then the dot product, so A dot B equals, well, 1 times 4 plus 2 times minus 5 plus 3 times 6. So there's going to be 4 minus 10 plus 18, which is 12. So for now, this number does not have any interpretation. Why this is useful, we will show in a bit, but this is how you do it. So it's a fairly simple operation. You take two vectors, multiply component-wise, and add those numbers together. And here you find 12. Okay, great. So just to finish off the definition, the dot product is also called the inner product or the scalar product. And scalar because we find a number. We will also see in another video that we also have something like a vector product or an outer product. So it's a number, A dot B. And sometimes it's also written with these brackets. So in hand written that would be A comma B. So that's exactly the same as A dot B. Depends a little bit which notation is being used. In literature you find both of them. So I'm going to do a little bit more properties, if you like, before I'm going to actually use the dot product. So first, a couple of properties. They look a bit dry here, but they make sense. So what do you do, A dot B or B dot A? That doesn't matter, because if you multiply two numbers, the order in which you do that doesn't matter. 2 times 3 is the same as 3 times 2, and here you do that a bunch of times. If you do the dot product of A dot and then in between brackets B plus C, you could also do A dot B plus A dot C. If you write it out, you will easily find that. You can also multiply with some number alpha, and then you can put it in front of the dot product, or you can put it in front of one of the two vectors. It doesn't matter, you find the same thing. If you compute the dot product with the all zero vector, you find 0. And finally, that's a little bit interesting. If you have a vector and you compute the dot product with itself, you find a 1 squared plus a 2 squared plus a 3 squared, which is precisely the length squared. So these are general properties that can be useful if you want to do computations with dot product. Okay. Now, then the reason why we have an interest in this dot product, what can we use it for? So it is extremely useful for computing angles. And I'm not sure if you ever thought about that, but if you're in general, if you're in 2D in a plane and you have two vectors, then it's not so difficult to compute the angle between them maybe. But in space, in 3D, well, if you just take any two vectors, it's quite hard. I mean, of course, we know that there is a plane going through these two vectors, and then we could, in principle, just look inside that plane. But how to do that if you're actually doing computations with vectors, that is not so easy. So here, the dot product turns out to be extremely handy. So let's say that we have two vectors, A and B. And let's say that between them, they make an angle theta. So here I plotted them in the same plane, but they can be anywhere in space. The angle between them is theta. Then what we have is that if you compute the dot product, so this number 12 on the first slide, that is equal to the length of A times the length of B times cosine theta, so the angle between them. So the way that we actually normally use that is in the sense that we basically have here, that I can rewrite this as cosine theta equals dot product of A and B over length A times length B. So if you give me two vectors in space, then it is almost trivial to compute this dot product. I can also compute the length of A and the length of B. So then I have the cosine of theta, and then I have to look for which angle theta this cosine is being reached. So that is how in practice we will use the dot product. And you have a bit of freedom because we have seen that the cosine function is periodic with period 2 pi. So usually we make the choice that theta should be in between 0 and pi. And since you can add or subtract 2 pi, you can always have that. So let's look at, well, let's first try and get a bit of confidence in this formula. So I'm going to look at an example where I'm going to check this formula. So let's say that we're in space. So I have an x-axis, y-axis, z-axis, and I'm going to pick two vectors, but I'm going to pick them a little bit special. So I'm going to pick this red vector, which is the vector from 0, 1 with components 0, 1, 0. I'm picking a second vector b, which is going to be 0, 1, 1. And as you can see, I'm cheating a little bit in the sense that I pick an example where this is 0 and this is 0. So both of these vectors have an x component which is 0, which means they're in the yz plane. So basically my paper is the yz plane, and I know the angle now. So the angle between them, I can just read it off in the graph. That's the angle between these two vectors. So that is the same as if you were in the normal xy plane and you would have this vector and this vector. And then you see that this is a 45-degree angle. So we know that theta equals pi over 4. So the angle here is pi over 4. So I want to check whether my formula also gives this. So the formula from the previous slide was that the cosine of theta equals the dot product A dot B over length A times length B. So this should hold for any vectors in space, also for this particular case where I chose the x components to be 0. So this is the dot product in between 0, 1, 0 and 0, 1, 1 over, well, the length of A is 1. And the length of B is the square root of 2, because B has components 0, 1, 1. The dot product is 0 times 0 plus 1 times 1 plus 0 times 1. So this is going to be 1 over the square root of 2. And if you multiply the numerator with the square root of 2 and also the denominator, then you see that this is the same as a half square root of 2, because in the denominator it says 2, so this is a half square root of 2. So which angle theta has cosine equal to a half square root of 2? That's pi over 4. So indeed, we find that theta equals pi over 4. So that gives us a little bit of confidence that this formula indeed holds. Now, let's look at a couple of special cases now. So I'm going to pick special A and B and see what this formula here, so this one, the red circled one, what it's going to give me. So first of all, so here's the same. This is the definition, this is a property of the dot product. That was the theorem. I've rewritten it to find the cosine of theta. And now let's pick B equal to A. So what we then find is that the cosine of theta is A dot product with A. So that's the length of A squared, as we have seen. This is also the length of A squared, so we find 1. Cosine theta equals 1, that is theta equals 0. So indeed, if we have a vector A, and then B equals A, so if you compute this dot product, we see indeed that the angle is 0. So that's great. Now, let's take A and B parallel. And we have seen in the previous video that means that B is C times A for some C, and 3 situations can occur. We can have A, and then we can have that B points in the same direction. That's the case C is bigger than 0. We can also have the situation that we have A and that B points in the opposite direction. C is less than 0. And then the third case, which is a bit boring, is that C equals 0, and that means that the B vector equals 0. So I'm going to look at those cases and see what the boxed formula here gives me. Okay. So first, let's take C positive. So A and B, they point in the same direction. So then we have something that is a bit similar to what it says here. This was the situation with C equal to 1. So here we have A dot product with CA, that's C times the length of A squared. In the denominator, we can pull out the C, put it in front of the length, and we see that we have 1 again. C over C is 1. So theta equals 0, that makes sense because they're both pointing in the same direction. Now, let's take this situation. We have a vector A, and now C is negative. So that means that B points in opposite direction. So we immediately see here that the angle theta is pi. And indeed, what you get now is here, this is the same as we had before. In the denominator, this here, because C is a negative number, if you pull it out of the length, out of the double bars, then we get the absolute value of C. So just maybe to make that a little bit more clear, you could think of the situation that, for instance, just as an example, that we take C equal to minus 3. So it means that we have a vector A, and we have a vector B, which equals minus 3 times A. So it points in the opposite direction. Okay. We know that the length of B is the length of minus 3 times A, and that is 3 times the length of A. So if you pull the minus 3 out of the length, you should put an absolute value sign there, because lengths are always positive. We don't want negative lengths. That does make sense. So if you compute this thing here, then for the dot product up here, you would get, so if you would here do A dot B over length A times length B, you would find minus 3A dot A in the numerator, and you would find length, you would find length of A times 3 times length of A, because 3 times length of A is length of B. So together, what you get is minus 3 over 3, which is minus 1. And here, the dot product of A with itself, that's precisely length of A times length of A. So they cancel against each other. You can strike this one for these two. So here, I picked C equal to minus 3. And in general, if C is negative, you always find minus 1. So cosine of theta equals minus 1, theta equals pi. Okay. So now we have C positive, C negative. There is one more case, which means that C equals 0. And I didn't put that here, because if C equals 0, it means that B is 0. And then we would find here 0 equals 0, and we don't have any information. The angle is not really defined, right? If you have the 0 vector that doesn't have a direction. There is one more interesting case, which is if A and B are perpendicular. So they make a 90-degree angle. So if A and B are perpendicular vectors, then the angle between them is pi over 2. So we have some vector A, and perpendicular to that we have B. And here is a 90-degree angle, or pi over 2 in radians. So what we then find is that the dot product of A and B is length A, length B, cosine theta. And cosine theta for the theta equals pi over 2, that's 0. So apparently, if two vectors make a 90-degree angle, like here, their dot product equals 0. So let's put that as a corollary. A corollary is like a consequence of a theorem. So you have a theorem and then something follows from it. That's in mathematics called a corollary. So vectors are perpendicular if and only if A dot B equals 0. This if and only if, that's also a mathematical term. What it means is if A and B are perpendicular, then that dot product equals 0, and the other way around. So also if that dot product equals 0, then they are perpendicular or orthogonal. They make a 90-degree angle. And the short notation for that is this thing here. So AB perpendicular. And it is a very easy way to check that. So if you give me two vectors and you want to know whether they are orthogonal or not, just compute the dot product and you immediately know whether that is true. So two more properties of the dot product. First, the Cauchy-Schwarz inequality, and that says that if you take the absolute value of A dot B, that is less or equal length A, length B, and that makes sense because we have seen that A dot B is length A, length B, cosine theta. So we have that the absolute value of A dot B is length A is a positive number, length B also, times the absolute value of cosine theta. Now the cosine is always in between -1 and +1. So if you take the absolute value of the cosine, that is less or equal 1. So this is less or equal length A, length B times 1. So that proves the Cauchy-Schwarz inequality. And then the triangle inequality says that the length of A plus B is less or equal length A plus length B. And that also makes sense because what we basically have, we have seen that if you have a vector A and a vector B, that you can find A plus B by drawing this parallelogram. So here we have A plus B. And basically what this triangle inequality tells you is if you start here and you want to travel here, that this is the shortest path. Because if you walk directly, you have a certain length. And if you do first this length of A and then this, which is length of B, then it takes you longer. And the only situation you can imagine when they're the same is if A and B are parallel. So then you would have an equal sign here, and otherwise it's a smaller sign. So that is what the triangle inequality tells you. Now let's wrap up this video by looking at an application. And in this application, let's assume that we're going to pull a wagon. So we have a little wagon here, and there is a person who is pulling it with a string. So this is the string, and this here in red is the force that this person uses to try and move the wagon. Now, as you know from vectors, you can decompose this vector into a part that is parallel to the ground and a part that is orthogonal to that. If you want to move the wagon, the only part that is interesting is this part here of the vector. So let's see if we can compute that. So let's try and decompose this f vector here into a horizontal and a vertical part. Note that I made the f here and here also bold, since they are still vectors, but they only point in horizontal direction or vertical direction. So this one, for instance, will have a non-zero x component and a 0 y component. So we could put the angle theta here, and then we could consider this triangle. And then we know from the rules of sine, cosine, and tangent that in this triangle, it has, so this triangle here has a 90-degree angle. So I know that the length of the long side, this one, let's see, from the triangle, I know that the cosine of theta, cosine theta, is the length of the adjacent side. So that's this, over the length of the long side of the hypotenuse of the triangle. So if you rewrite that, you see that apparently length of f times cosine theta gives me precisely the length of this horizontal component. So the horizontal force is this length times I, and I, hopefully you recall this I here, is the vector with arguments 1 and 0. So what we have basically is that F, the horizontal force, equals a 2 vector. First component is length of F times cosine theta. And the second component equals 0. Now here we have everything nicely aligned. We can generalize this a little bit. And the more general question that I'm going to ask is this. Suppose I have two vectors A and B. And now what I would like to do is decompose my A vector into a component that points in the same direction as B, plus, well, basically the rest. Because if I do that, if I find this V, then I know that A is the component that points in the same direction as B. That's what I called V, plus W. So if I have found V, I already know that W equals A minus V. So the question is, how can I find this V component? How can I do that? So let's write that down. given are A and B, and what I would like to find is the component of A along B, and that is just a mathematical name of this V vector here. So I'm going to write my A vector as V plus W. So V points in the same direction as B, and it's called the part of vector A along B, or the projection of A onto B, and the rest. So W is just A minus V. And as you can see from my picture here, W and B make a 90-degree angle. They're perpendicular. So we have just seen some notation for that. So what we have is that W is orthogonal to V, and also W is orthogonal to B, because V and B point in the same direction. So some names here. Actually, I was going a little bit too fast, sorry about that. Let us try and derive the equation for that. So let us try to find a formula for V. And again, like I did on the previous slide, I'm going to look at this triangle here. And as you can see, the cosine of theta is the length of the adjacent side over the length of the long side. So what we have from the triangle is that the cosine of theta is the length of the adjacent side, V, over the length of the long side, which is A. So I have that the length of V is the length of A times cosine theta. Now, I normally do not have a direct expression for theta. So I would like to find a formula that does not involve theta. So what I'm going to do is the following. So theta is the angle between A and B. So I know that the dot product A dot B equals length of A times length of B times cosine theta. If I combine these two, let me get rid of this here. So I have here from this formula that cosine theta is A dot product B over length A times length B. And I'm going to plug that into formula for the length of V. So I now have that the length of V is the length of A times, and then I plug in the expression for the cosine theta, A dot B over length of A times length of B. And you see that I have a length of A in the numerator and in the denominator. So I can write this as A dot B over length of B. So I'm already quite a long way here, because I now know that my V vector, the length of this blue vector here, so this length is given by this formula. And now I want to make it a vector, so I also want to know in which direction it points. And it points in the direction of B. So it would be tempting to say that my vector V is now this number times B, because then I have something that points in the direction of B, but that's not completely correct yet. Because if I want to have a vector that points in the direction of B and has precisely this length, then what I should do is compute the green vector u here that has length 1 and points in the direction of b. And we know how to do that because we have seen that in a previous video. If I take u to be equal the vector b over its length, then I know that u is a unit vector, so a vector with length 1, unit vector in the direction of b. And I've now got all the bits and pieces that I need, because I now know that my v vector, v, is the length, so that's this number here, so I'm going to put that in there, a dot b over length of b times u, so that's a vector with length 1 pointing in the correct direction. And then finally I'm going to take this expression for u and plug that in, and then altogether we have a dot b over length of b squared, because there is a length of b here and a length of b here. So if I take them together, I find a square times b. Let me just put brackets here to indicate that in between the brackets is a number, and that is the length. And this is the direction now. So the slide got a bit messy. Let's go to the next one where I put that in blue boxes. So what we found now is that the component of a along b, that is precisely the length of v. So that's the dot product of a with b over the length of b. That's a number. And then the projection of a onto b, that's a vector. So also the project here is in boldface. So that's the v vector. It is a dot b over b squared times b. So this here is a number and this is a vector. And we can use that in a number of applications. So let's end this video with an example where we do this with numbers. So let me take a new slide. And the question that I'm going to answer here using what we have just seen is, say we have the vector, oh, let's do that in blue. We have the vector a, which is 0, 1 over 8 and 4. So it's a vector in space. B is the vector 0, 4 and 3. And I would like to have the projection of a along b. So as you can imagine, this is quite hard to draw, right? Because we have two vectors. Well, we can still do it here because again, this is a special case, x equals 0. So if I do it like this, x-axis, y-axis, z-axis, then we have the vector a is 0, 1 over 8, 4. So that's something like this, a. So here along the y-axis, this is 1 over 8. Up here is 4. And then we also plot the b vector, which is 0, 4, 3. So that would be something like this. It's just a sketch, it's not to scale. So it make them a bit longer. This is 4, and this should be 3. My picture is not very good, sorry about that. And then what we're going to do is project it. So I'm interested to find if you do the orthogonal projection here. So this is a 90-degree angle, then you find a vector in blue here. and this vector is the v vector from the previous slide that we're interested in. And apparently, so I call this v, and with the results from the previous slides, what we get is a dot b over length of b squared times b. So the dot product between a and b, that's 0 times 0 plus 1 over 8 times 4 plus 12. So that's 0 plus 4 over 8 plus 12 over, well, the length of b squared is 16 plus 9. And that is a number, as you see, times 0, 4, and 3. And if you compute that, you find that this equals 0, 2, and 3 over 2. So I didn't do all the intermediate steps, but I'm sure you can do that. The component, so the length of v, you can also compute, and that is, so the component of b along a equals a dot b over the length of b. And if you compute that here, you would find 5 over 2. And this 5 over 2 is precisely the length of this v vector, so you can verify that. I'm not going to check it here. Then what you would also find here is if you would now compute, say, a is v plus w. If you compute w as a minus v, and I recommend that you do that on a bit of scratch paper, then what you should find is that w is this vector. I'm also going to make this a little bit thicker to hopefully make it clear. So this is w. So the a vector, this red vector here, is the v vector plus the w vector. And if you compute w, then what you should find is that w is orthogonal to b. And w should also be orthogonal to v. So you can check that, you can verify that and see what it is indeed holds true. And I think that for your understanding would be good to do so. So try that. Try to see if w is orthogonal to b. So a bit of homework there. I'm going to wrap up this video. What we have seen is, given two vectors in space, how you can compute the dot product. And we have also seen the relation between the dot product and the angle between the two vectors, and how you can use that to compute the component and the projection of one vector along another vector. I hope this was clear, and I look forward to seeing you in the next video.